So this is an example for us to understand how to incorporate biological and chemical transformations or reactions into our stock and flow diagram to follow our modeling process. This is an example of typical management of acid mine drainage at a metal mine. So, acid mine drainage is a worldwide problem that pollutes water streams. And why is this happening? Is because when mining activities are happening, you start exposing pyrite, which is this component. You start exposing this component to oxygen. And when the conditions are, when oxygen is present and also we have wet conditions, this process, bacteria start transforming the pyrite and it start producing a sulfuric acid. And then this sulfuric acid will decrease the pH of this stream of this acid mine drainage, which allow the solubilization of metals, other metals that are in present. So if there are metal precipitates or metals in the environment, as in minerals, with the acid, they start getting released. The typical color of the acid mine drainage is this, and this is a picture that I took from acid mine drainage formed from mine residues in Tasmania. It is it's a significant problem, environmental problem, and also is a problem that need to be tackled by mining and metallurgical companies, because the process can last if there is enough pyrite. The process can continue for years and years. So there's gotta be a way to control this oxidation, and the way that they do it is they put the pyrite into ponds where they or lakes where they actually cover this pyrite with water. And why is this for? Well, water will be like a barrier for oxygen to be directly transferred into and be in contact with pyrite, and to avoid this reaction to occur. But of course, we know that the oxygen can be transferred into the water, and the velocity at which the oxygen is being transferred into the water will control the rate of pyrite oxidation. Then once you are producing acid mine drainage, you need to treat this water. How is this usually treated? Well, they usually use sodium hydroxide, so they treat it in treatment ponds, and they add directly the sodium hydroxide, and then they neutralize. This is with the aim of neutralize the pH. And with the neutralization of the pH, you also have the precipitation of metals. So acid is generated by the oxidation of pyrite. The rate of oxidation is controlled by the rate in which oxygen transfers into the water within the void, and is given by this equation. And this equation involves the film transfer coefficient, the area, the surface area, and the delta of concentration of oxygen. And that delta of concentration is given by the concentration of oxygen at the saturated point, saturation conditions, minus the concentration of oxygen. We're going to assume for this example that oxygen is consumed immediately by the oxidation reaction, and therefore the concentration of oxygen is equals to 0. So what we want to know is how much acid is being generated, and all the reactions that we have, that we will show you, will be controlled by this rate. So this is the only value that we have, this rate of oxidation. These are the reactions. The first reaction is the one that I already showed you, which is the pyrite oxidation. The second reaction is a neutralization reaction in the treatment pond. And we are going to calculate the amount of hydrogen, sodium hydroxide that we require for the neutralization. But how are we going to define whether we need to neutralize or not the pH, the value, the acid mine drainage or the liquid, the stream, the liquid that is in the pond? We need to estimate the value, the pH in the stream. So we all know that pH 7 is considered a neutral pH, and a pH below 7 is considered to be acid. So we're going to develop the stock flow equations for each component of interest. So now you can start guessing which are the main components that we're going to care of in this problem. So the main stocks that we will have will be the pyrite, obviously, because that's the one that controls or will release the hydrogens that will decrease the pH, and the other stock will be the hydrogen. Because it will rule the amount of sodium hydroxide that needs to be added to the treatment, to the pond or to the void, in order to neutralize the pH. So, for example, the mass of pyrite consumed in mine void will be equal to the rate of oxygen transfer times a yield, and a yield of mass of pyrite per mass of oxygen, and that will be given by the first equation. So then at the end we will have units of pyrite, right, instead of units based on oxygen. So this is a step that you are going to follow for each of the reactions.